All right, we are going to take a look first at a practice problem on page 393 in your book. We're going to take a look at number 1 so you guys can see how to approach these questions. So we want to write a thermochemical equation and the equation using a delta H notation with the smallest possible whole number coefficients for the following chemical change. So we want to write a chemical reaction first for the change that it's talking about. So in this case, it's talking about the combustion of C2H6 gas. So we need to write a combustion reaction. So we're going to start with that C2H6 gas as our first reactant. Now, a combustion reaction always follows the same pattern. We should know this part. Learn this in Honors Chem as well. We have our hydrocarbon. We add oxygen as so those are fuel sources. So our fuel plus oxygen, and it's going to always make carbon dioxide gas plus water gas. When we burn stuff, it's all gas. And we're going to go ahead, and I like to put my blanks there so I can balance my reaction. So let's check out balancing it. We've got 2 carbon on the left, so we need 2 carbon on the right. So I'm going to go ahead and put a 2 there. I have 6 hydrogen on the left, and so I'm going to need 6 hydrogen on the right. So I'm going to put my 3 there. And then we need to balance our oxygen. So we have 4 total here, plus 3 here. So we need, that gives us 7 oxygen. Now, we've got 2 over here, so technically we would write 7 halves. That is 7 halves of the oxygen molecule would give us 7 oxygen atoms. But that's not whole numbers. So if we wanted to make these whole number coefficients, we could take everything and multiply it by 2. So I'm going to take off what we had. So this was a 1, so it becomes a 2. 7 over 2 times 2 becomes 7. We had a 2 here before, so that becomes 4. And we had a 3 here before, so that becomes 6. And now we have our smallest whole number coefficients. Now, to write this as a thermochemical equation, we need to add in our energy. First thing we notice is that our energy is negative, so it's going to be a product of the reaction. It is exothermic, so it is producing heat as burning things does. So the energy is going to be on the right side. Now, it's producing this much energy per mole of C2H6. We have 2 moles of C2H6, so we're going to need to double this amount. So if we multiply that by 2, and do that as a little side calculation, 1428 times 2, we get, let's see, 2, 4, 5, 2 times 4 is 8, and 2, 2856. So we're going to also add 2,856 kilojoules per mole of the reaction. So when we incorporate this energy into the reaction, this number will be produced every time this reaction occurs as written. Okay, so per mole reaction is how we can also write that. So every time this reaction happens once, we produce 2,856 kilojoules of energy. So that is our thermochemical equation. Thermo meaning heat, so we've got the heat, we've got chemicals there. So that's our thermochemical equation. We also want to write it in the delta H setup. So I'm going to do that. We're going to have the same reaction. That doesn't change. 6 water. Calculations a little in the way. And then to the side, instead of writing the energy as part of the reaction, we write delta H. And then we have our number, 2856 kilojoules per mole reaction. But we're going to indicate if it's endothermic or exothermic with a positive or negative sign. We saw earlier that it is negative, it is exothermic, so we're going to make it negative. So these are the 2 ways that we can represent that equation. If this was a positive value, then we would incorporate it into the reactant side. If it's negative, we put it as a product. Now you have 2 more questions. dealing with the formation of a chemical and the decomposition of a chemical. So when we decompose something, we're breaking it down into its elements. So that next one has NH3, so we'd want to break it down into nitrogen and hydrogen. But we want to think about, are those Hofbrinkel ones? Do those come in pairs? How would we write them? And then balance our reaction. Same thing with the formation of HBr. So it's forming that, the HBr should be your product. And then it should come from hydrogen and bromine. And think about, are those Hofbrinkel ones? Do those come in pairs or not? And how would we write them? Okay? So think about that, try them out, and we'll check them in class.